Well, we have been looking at the atom and quantum theory and how the atom is structured, and we know at this point that the atom consists of a nucleus of positive charge with electrons flowing around it that are negatively charged, in such that normally the electrons balance the negative charge, the positive charge of the nucleus, so the atom on a whole is neutral electrically. We're now going to start chapter 41, and in particular chapter 41.1, and talk about nuclear theory and go inside this nucleus and see what's there and how this affects our knowledge of science. First of all, what is a nucleon? Well, the nucleus is composed of both protons and of neutrons. The neutron is electrically neutral, and the proton is positive. We didn't know about the neutron for a while. We didn't realize it was almost like a proton, except it's electrically neutral. It weighs a little bit more. You might think that the proton having a positive charge would cause it to weigh more than the neutral particle, like you have a neutral thing and you add the positive charge and it weighs more, but the reverse is true. The neutral particle weighs more. They're very similar in behavior, and the proton-proton attraction, neutron-neutron attraction, and the proton-neutron attraction are almost exactly equal, as we'll find out. Well, anyway, this nucleus is made up of both these protons and neutrons, and these are called nucleons. So a nucleon is kind of like a sibling, is either a brother or a sister. It's either one of these. And it was first discovered, neutron was not discovered until 1932, and that was done by Chadwick. And as I said, the neutron has a mass slightly larger than the proton. Really, all of the mass of the atom is contained in the nucleus. The electron only weighs 1/18,000th of a proton, and therefore this nucleus totally dominates just with the protons alone. Then it has an almost equal number of neutrons. So the electrons are truly negligible in the mass or weight. We use the symbol Z for the number of protons and A for the number of protons and neutrons. So Z is equal to the number of protons, and A, this is called the atomic number, and it is the thing that characterizes an atom or a chemical. If you have a given number of protons, that is what tells you whether you have zinc or copper or iron or whatever. And then independently of that, you have more neutrons. You have neutrons in the nucleus. And if I add the number of protons and the number of neutrons together, I get the mass number, which makes sense because remember the mass is contained in these protons and neutrons. So, and since they're kind of very similar in mass, they don't differ too much. A really gives us kind of the mass of the nucleus and therefore of the atom. The designation of a nucleus is written in a particular way. You'll notice that whereas X is the chemical element, as we have right here, what we do is we write A up here and Z down here. So we write A, Z, and then the chemical element, which might be something like hydrogen. Well, hydrogen, for example, can come in 3 different flavors. It can come, we could have hydrogen, it always has 1 proton, but it could have it could have just 1 proton, and therefore it would have an A of 1, or it could have a proton and a neutron. It has to still be hydrogen, so it's only got 1 proton. It could have 1 neutron, that would be this, or it could have 2 neutrons, and then it would be this. And so forth for all of the elements, and there is some redundancy between the chemical symbol and this number down here. They have to agree. This 1 is for hydrogen, 2 would be for helium, and so forth. Isotopes are nuclei with the same number of protons but differing number of neutrons. So these are all isotopes of hydrogen. And it turns out that you can have an element like hydrogen has 1 proton, but it can have none of the neutrons, 1 of the neutrons, 2 of the neutrons, 3 of the neutrons, whatever. However, as you change the number very much of neutrons from the number of protons. If they're not approximately equal, the substance becomes more and more radioactive and therefore unstable. Now, the nuclear forces, as I mentioned a while ago, are felt about equally from both the neutron and the proton. So they behave almost like identical particles, except that the proton has electrical charge. We defined the binding energy, very important concept, to be equal to the total of the amount of energy needed to separate the nucleus into separate pieces. So this is if you were to take one of these nuclei and rip the protons and the neutrons apart and take them out to a very large distance, then the total energy required to do that is called the binding energy. And of course, the binding energy per nucleon is the amount of energy it takes to take that single nucleon out. For example, the binding energy here of that second neutron would be how much energy it takes to take that one neutron out of the nucleus. The binding energy is similar to the ionization energy that we had for an atom, where we have an atom like hydrogen and we take one electron and take it to a very great distance away. And you remember that energy was 13.7, as I recall, 13.6, 13.7 electron volts. Now, the mass defect is the binding energy expressed in terms of the mass equivalence by virtue of E equals mc squared. Basically, what you do is when you bring these nucleons together, the protons and neutrons, and build a nucleus, as you build that nucleus, then of course they bind together and they lose energy. But they lose so much energy that there's actually a difference in the mass. So a nucleus, say of carbon, might be carbon 612, because carbon has 6 protons, and it has a normal isotope has 6 neutrons, so that's 6 and 6 is 12 protons and neutrons. If I think of all of these 12 protons and neutrons, as I bring them together into the nucleus, they lose energy. Energy is given off in radiation or heat or some other manner, until finally these are bound very, very tightly together with one another. So tightly together that 12 individual protons and neutrons weigh much more than the nucleus weighs. Actually, this occurs with an atom too, but it's so small of an effect that we never really see it. So the mass defect is this binding energy expressed in terms of the mass equivalence, how much mass we have lost. And the binding energy per nucleon is greatest in the mid-range of around iron and less in the light elements like lithium and in uranium. Now let me explain how that is. If I look at the binding energy, this would be binding energy per nucleon. And I look at A here, which is the number of neutrons and protons. Then in fact, this goes up like this. I could put Z here just as easily. Look at the number of protons. It goes up and then it comes down like this. And right here in the center is iron. It means that out of all of the different nuclei, iron is about the most stable. It has the strongest binding per nucleon of any of the elements that we have, or any of the isotopes, I should say. That means that down here we always have an advantage to take hydrogen and helium and up here to have uranium and try to get closer to this iron. Here we have fusion, atomic nuclear fusion, where we can take 2 hydrogen atoms and squeeze them together and get helium, 2 helium, and get other nuclei that are closer to iron. And this is actually how stars work. They work by fusing the hydrogen and helium to get closer and closer to iron until finally they have some, almost all of the other elements are made, by this process. Now over here, just like you can make a hydrogen bomb by combining hydrogen and helium together, you can make, through fusion, you can have fission and break apart uranium and some of these heavier ones and get back toward iron. So we have fusion this way, fission this way, takes us more toward iron and takes us more toward a stable nucleus. Say here that the greatest binding is around iron, and we need to know approximately what the radius of the nucleus is, and the radius of the nucleus is about 1.2 e to the minus 15th and times a to the 1/3. Let's see if we can make sense out of this. This says that to a good approximation, a, let's say a is 1. So we've just got something like a proton. Then a, the cube root of 1 is 1. So you might say we start out with nuclei that are real light that have a size of about e to the minus 15th. That's the radius. Well, this is called a Fermi, or a femtometer. We had this in a previous lecture, and it's 10 to the minus 15th meters, or equivalently, it's 1 e to the minus 15. Now, to give you some perspective here, you may recall that the atom itself is about 1 angstrom. That's 10 to the minus 10th meters. And therefore, the nucleus is about 10 to the minus 15th across. So, this is mainly empty space inside the atom. You mainly have a nucleus, which is 10 to the minus 15th, and then the electrons are evolving at a distance of 10,000 times as great. Out here, that's 10 to the 5th difference between here and here. So that's a huge difference. Actually, a 10 to the 5th would be not 10,000, but 100,000. So this is a huge difference. So this is mainly, the atoms are mainly space inside. So you need to remember the following. You need to remember that a Fermi is a femtometer, and a femtometer, or a Fermi, is 10 to the minus 15th meters. And the radius is given by about a femtometer times a to the 1/3 power. Why the 1/3 power? Because if I get spheres together, and I put them like this, then of course the radius of those spheres goes as the cube root of the number that I have. Just like if you're counting marbles in a jar and trying to estimate it, then if you look at this, if you know the size of the marble and you can look at the size of the jar or the volume of the jar, you can say, oh, the distance out should be about 1/3, or the cube root, power to the 1/3, cube root of the number of marbles that I have in here. That's because you're building in 3 dimensions, and that's why you have the cube root here. So the things to remember are the nucleons are either protons or neutrons. They have about the same mass. The neutron was discovered in 1932. Up until then, we didn't even know it existed. This is the designation for a nucleus. And when you're talking nuclear physics, you almost ignore the electrons. They're so lightweight, and it doesn't really matter. You can have more or less electrons just giving you ions of that particular element. The element is characterized by Z, which also tells you what the chemical symbol is, but it doesn't tell you what A is, because the number of neutrons can vary, giving you different isotopes of that same element. These protons and neutrons are bound together with some binding energy. This binding energy is huge, and it actually, by E equals mc squared, it results in a mass that is less than you would normally have if you weighed those objects separately. And you want to, of course, remember what the size of the nucleus is, and if you have something that's very large, then of course this a to the 1/3 makes some difference, and it's a factor of the cube root. Remember also that iron is your most stable nucleus.